And let's go to our dot. And now I want to see what happens if I rather introduce this in a counter current manner. So let's just get rid of this block there. In a counter current scenario, and this is explained on page 501, the procedure I am going to use now, in page 501 in your textbooks. Oh wait, I actually have it here. Hang on. If it works out well, yes, I do. Right, so let's just focus on this screen for now. So what we want in counter current, what that means, and I am sure you can all recall that from your CIO days, is I now have my fluid, my reacting fluid flowing in this direction, and my coolant is now going to be introduced on the other side, so it flows in a counter current manner. So if I start integrating from volume is equal to 0. At the inlet to my reactor, I have my Fi naught and I have my T naught for my fluid streams. But at the inlet to my reactor, I have the outlet, temperature, TU out. And this is the TU in, or the TU naught. So on this side of my reactor, where my volume is 10 cubic meters, or my 100 liters, there is where I have my temperature of my utility equal to 298 Kelvin. Okay, so what Vogler now says here, and he gives the equation, he says this is the energy balance for your utility. So he's derived it, so we are just going to employ that energy balance. The only difference is the sign. So instead of the minus sign over there, from the perspective of our, say, if you just look at that, instead of having the T minus T utility, the sign is going to swap. So let me just show you over here. Where is it? Yeah. So that minus sign that I had for my co-current one is now going to fall away. So this energy balance, you can read up, go and read this page in Vogler to make sure that you agree with that. Very simplistic way of solving, and that's going to suffice for our design applications that we want to use in this course. So what this now means is Vogler says you now need a trial and error kind of solution. So you are going to have to assume a coolant temperature at the entrance. So we're going to guess the coolant is going to come out at some temperature. And that is going to be our inlet temperature that we are now going to have to update. So we are going to guess a coolant temperature where it comes out. But where it comes out is where everything else goes in. So this is the start of my integration boundaries. And we are going to ask for the code to constantly give us the outlet value there. And we are correct with our guess value as soon as this outlet temperature of my utility is what it actually is at the outlet. So what the temperature is that I've got the cooling water available. Capish, can I get some questions or some thumbs up or something? Can we start trying to do that? Hello,
morning,
are you still there? Yes.
Sorry, do you mind
Who's
just going over that again? It's Josh.
Okay, cool, Josh. Of course, I will, but let me just clean it. Let me just create a clean slate. The large eraser, Kadush. No, I don't want to erase everything, so that's not going to work. Medium eraser. Let's go for, oh my word. Okay, and, oh, Nia, now I've undo, Control Z, Ish. Okay. Sorry for that. A small break, pause in transmission while technical difficulties are being. There we go. Let's do it with a small eraser. I'm going to do it slowly. Erase slowly and then speak. Try to speak slowly as I explain what is going to happen. Right. My utility. So this is how my reactor, let's use red for my actual fluid. So my fluid comes into my reactor at the inlet side, at where I start, where I use my boundary for, if I integrate, so if I solve dt dv, right? And I have dt is blah de blah dv. I start at 0 and I go to my final volume. So at this point where I start at 0, okay, so I know that my temperature there at the inlet, temperature of my reacting mixture is equal to my T naught. And that is that 320 that was specified. Your reactants come in at 320. But now my utility is coming in at 298. That's the inlet temperature to my utility. But my utility, I feed, look at the arrows. It is on the shell side of my heat exchanger. And where I added, this is where my utility's temperature is 298 Kelvin. So it comes in where volume is equal to 100 liters. It comes on the other side of my reactor. So if I look at my reactor like that, with all the tubes there, this is the side where I feed my, there we go, and this is the side where I feed my utility. So this is counter current flow. In other words, I feed my utility there, 298, but I can't use this as the temperature where volume is equal to 0, because volume is equal to 0 is where that temperature is equal to the inlet conditions, and I've got 0% conversion. I'm going to feed my utility at the point in the reactor where my conversion is at its highest. So in other words, I cannot use T0 298 as the inlet temperature to my reactor. So I know it's the inlet, but don't think about it as inlet now. Think about the temperature at the point where the volume is 0. So at the inlet of the utility, it enters the reactor at the point where the volume is equal to my 100 liters. So at the outlet from the perspective of my reacting mixture. And it exits, so its temperature of my utility at the where it comes out will be at the point where my volume is equal to 0, where my integration boundaries is such that the volume is equal to 0. So this temperature is an unknown. That temperature is an unknown. It depends on the amount of heat that was exchanged between my fluid and my utility as they cross each other's paths along this volume of my reactor. And I need to integrate it from a point where volume is 0 to a point where volume is 100. And sorry, not 1,000. And at volume is 0, I know the inlet temperature of my product, reactor mixture, that is 320. But I do not know the temperature of my utility. So I have to go and give a temperature, because my integration boundary starting at 0 and going to the volume of my reactor wants a utility temperature at the point where the volume of my reactor is 0. It wants a temperature there, but I don't know that temperature. So I'm going to have to guess that temperature. What I do know is I know the temperature at the outlet of my reactor. So I know the temperature where volume is equal to V or X. I know that my utility must have a temperature of 298 when it achieves that point. So I can't use 298 for the temperature as it goes from volume is equal to 0. Better?
That makes perfect sense.
So essentially,
yes, go for it. Next speaker.
Okay, so essentially we're going to check the plot of the coolant temperature.
Yes, so we don't have to, we are going to plot it, but we are also going to specifically ask for a value there at the outlet so that we can check, and by trial and error, we're going to change our inlet temperature of utility. So remember, it's not the inlet temperature. When I speak about inlet temperature, I am not deliberately confusing you. It is the temperature of the utility at the point where volume is 0 from the perspective of my integration boundaries. Right. Okay, so let's do it. So what we are now saying is this is now not TU naught. This is now TU at V is equal to V of my reactor. Okay. So now I have to guess a TU naught. So I'm going to have to guess a TU naught. Where am I typing now? Let me just get a row. TU naught. I'm going to guess this. I'm going to do this manually. Of course, later on we can build it into a solver or whatever, but let's just see what happens if I build it manually. And now, what is a good guess value to use? So I will always compare it to my temperature of my reactants. So I would still want heat transfer to take place between that temperature and the temperature of my utility. So at the point they are in thermal contact with each other. So let's just guess a value of 310. So it is still 10 Kelvin colder than the temperature of my fluids at the point where my reactor volume is 0. And I must now just remember to change my energy balance for my utility. So I'm going to have the counter current version here. And I want to comment that one out. So I want to switch between them, counter current. There we go. So we have dPu, dV, and it is equal to, and now I have here A. Let me copy and paste it. I'm going to save you time. So I'm just going to leave out the negative sign there. You can go and look in Vogler for the details of this. Okay, so let's just have it print something for us so that we've got something easy to compare. So please print the outlet utility temperature. Utility from the PFR is equal to TU, so that we can quickly look at that. Let's see if it runs. Ready, steady, ka-ting. Yippee. Okay, right. So the outlet from our utility with that is 307. So what do we want that value to be? We want the outlet, so outlet is wrong. So let's just type it wrong. T utility, if T utility from PFR at V. X string is string. Right, string 2. Okay. So from the PFR at the V is 100 liters is 307. We want that temperature to be 298. Okay. So in other words, the value that we guessed is too high. It is too high. So let's just guess a lower value. Let's go to 305. 305. And remember, Python is patient. If I guess in the wrong direction, I will see I'm going in the wrong direction. Okay, that is 301. That is still too high. Let's go to 300. Ah, that is too low. Okay, so now we are getting somewhere. So I'm just going to change it to a very, let's say 301.5. Okay, so that's close enough for me. I'm going to stop here with that. You can now still play around with it, or you can write the solver, of course, and the return function from the solver. So you can run this in a fsol function, to which you send the T utility at where V is equal to 0, and it must change this value until the T utility at the volume out, this value is equal to 298. Or you can do it manually like this. So whatever works for you. This was quite quick to find that after playing around with it for a bit yesterday afternoon. But let's see what we have achieved. Not much. We haven't achieved much because we still have a very small conversion in our reactor. So what I am now going to do, so this is just illustrating the variables, and I can now, so listen, let's just pause with this U value. I cannot just change the U value and say, oh, but I want better heat transfer, or I want poorer heat transfer. So I am going to vary this until I've got the heat transfer that I desire. This is not something that you can actually decide on. So it is a typical value that I just used to get me started, but I must remember that the actual equation for that U is a function of the the tube side heat transfer coefficient and the shell side heat transfer coefficient, the thickness of the material of which I'm making my tube, and its thermal conductivity. So it's the material properties, the thickness of my tubes, and these two parameters, H out and H in, they are functions of like Prandtl and Sherwood and all those numbers, which is a function of viscosity and the linear velocity in my fluid, which in turn will actually be a function of the tube diameter that I actually choose. But we first just want to get a feel before, so I say, okay, let me just confirm now that I've chosen a tube diameter and I know the linear velocity and I've got my mass flow rate of my shell side. Now I can just corroborate that I do in fact get a U value. And so it will be a trial, not only in terms of trialing for that TU value, but the whole design procedure is an iterative procedure. So you will first check, okay, this gives me a more or less design. Now I'm going to fine tune and say, okay, so calculate a more accurate value for U with my given tube number. Rerun. Do I still get that? Do I want to change my tube size maybe? Stuff like that. Okay, so in your design project next semester, this is what I want you to keep in mind. In the part, you will see there's a part in the rubric that says I've integrated my heat exchanger design principle with the actual design of my reactor. This is what I mean by that part in the rubric. Right, so let's pause. So what I now want to do is I want to go back to my constant utility temperature. So let's do that. Constant utility. And I am going to blank that one out now. Checks. There we go. And I want to see what is going to happen if I have a utility, but I just preheat my feed by a little bit. So previously we said the maximum conversion we could get if I changed my inlet to 350 was 40%. So let's just see what happens in a 100-liter reactor for my constant utility. Okay, so this looks a bit more promising. So in 100 liters, it seems as if I can go past that equilibrium limitation of 40%. Okay, so I can now once again increase the volume of my reactor to see what will happen. There we go. Right, so I still go very slowly, but I go to a 50% equilibrium if I've got that constant utility. Let's check our higher temperature. So I'm now playing around with my design. I'm seeing, can I get something better out of this? Because simply adding this utility, cooling it down, yes, I can achieve a higher equilibrium conversion, but I am not using that initial nice fast rates that I can get. There's my plot there. That nice fast rate that I can get at the inlet to my reactor. I'm killing that by adding a utility. Unless I can maybe start with a higher inlet temperature of my fluid. Higher inlet temperature of my fluid. Oh, I must just change that, sorry. And change my utility temperature to 298. So do you all know why I'm now changing my utility temperature back to 298? I now have a constant utility temperature at 298. Let's just run my cell again. Okay, so run my cell again. Oh, yeah, no. So now I must make it. I was too excited. I can always have a warmer utility. Okay, and so okay, I want my utility to be at 310 Kelvin. But it takes work to get a utility at 310 Kelvin. I'm now going to have to blend it with something else. So I can't just get it from our cooling tower where the cooling water is produced. Water is being produced. It's being cooled to be at a specific temperature. I'm going to have to blend it with something, and then I know you all hate CPB for now, but then I'm going to have to build in a control loop in order to have my utility temperature at a higher temperature. So that builds some complexity into my design procedure. So let's just preheat our reactants. And let's just now the constant utility temperature, which is in any case not realistic. It's not the truth. So this is just something to make the modeling easier if I ask you or Vogler asks you about that problems. But now that you know, it's quite easy to build in the co-current and the counter current. There we go. Energy balances for my utility. So let me just do co-current and let's see what happens in my design. So now, okay, right, I go up to about increased my inlet temperature T0. So now still, I do not utilize those initial high rates. Let's see what happens with my, I've got a question, or is that a comment?
No, ma'am, I missed some questions, so I'm just asking.
Okay, all right. So let's do this, Philip. I'm just going to complete this whole wara of mine and then we'll pause for questions. So we've got the co-current now sorted and now I'm going to see whether it's counter current can make a difference. So counter current, there we go. And now I'm going to have to re-guess, of course, that inlet temperature of mine. So I'm going to re-guess that. So let's just see. Let's call it, so still want it colder than that temperature, so let's start at 320. There we go. Oh, 60. So what the hell? Now we are getting some interesting profiles. Look at this. Look at this. This is just by changing a button. Okay, but I'm lying to myself. I'm getting too excited because that temperature is slightly, it's about 5 Kelvin too high. So before I feel that I have achieved nirvana here, let's just change that temperature. It's still too high, so let's go to 310. There we go. Okay, that's too low. So of course I'm going to go to 315.5. Always a 0.5 somewhere. Okay, there we go. So I'm happy with that. So I can actually achieve a 70% conversion. It's very beneficial if I can employ this counter current. In other words, there where I want to have the highest rates, where I want to utilize the fact that I don't have much of my product available and I want to utilize the high rates that's possible. I don't want to kill that rate there by cooling at the maximum there. I don't want to cool, oh my word, power failure. Can you still see me?
Yes, we do.
Okay, all right. So I'm not sure what happened to the power here. Okay, so in other words, if I feed this counter currently, what it means is it's at the coldest point of my utility. Is there what I want to cool down in order to drive Le Chatelier? To say I am cooling down because I want to drive past that adiabatic equilibrium point. Okay, and there where my utility is at the warmest, so I allow the heat transfer will remember if I look at that, the rate of heat transfer or the slope of my energy balance is a function of that temperature difference between my utility and my flowing fluid. And therefore, at that inlet to my reactor, the true inlet where I now feed my products, I can still have that increase in temperature and then only do I start cooling down. And because I have the increase in temperature, I benefit from the high rates at the initial point in my reactor. So for volume, our target with our previous stats, that 4.2 with the 2 CSTRs was an overall 70% conversion, and we got about 180 litre reactor to achieve that. Now we can do that in 100 litres, and I can still play around with it, but still I had to increase this temperature of my inlet stream. Right, so let me I want to do something else here. On this plot of the utility, I want to include the temperature of the fluid. So let's just have them on the same axis set. So we've got this and I've got the temperature. Okay. Yeah, so that's now the orange one. What you must remember is if you model this stuff is I can't have, Python may be able to calculate it, but I can't have a point where I have a crossover in my heat exchanger or a pinch point, for instance. So let me just show you of a pinch point. So if I choose this to be exactly the temperature, 350. So this is now going to be wrong. This is not the correct solution. But here, there's no driving force for heat transfer because the two fluid streams that must exchange heat pinches at that point. And it can happen that pinch point happens along over this length of your reactor. And that is not permissible. That will not happen. So make sure that you take cognizance of that as you change your mass flow rate of your utility fluid, or you change the temperature, or some of the parameters. Plot the two temperatures. So this is now the temperature in my reactor. This is the temperature of my utility. My correct temperature was actually 315. 315. So that is at that volume point. 315.5. There we go. So I can see that my actual stuff, the warm stuff, is always warmer than the cold stuff throughout my heat exchanger, so that they can exchange heat with each other. Right. Okay, so let's go to this, and I am going to stop sharing my screen for now, so that I can see whether you have questions. Right, questions. Good conversion. Is 70% good enough? Yes, for integration, yes. But we said that it wasn't 320, no? It was about 315. Okay, I'll wait till the list is done. Okay, look. PFR where the volume is not for integration. So let's just go through that again. So I'm going to share my screen again. Share screen. Pink. Share. So it shouldn't be. So I started guessing at 320. I started guessing at 320. So what I am guessing now is, let's just add a clean add page. What I am guessing here is to say that I know, get the pencil out. I know there, my tube, okay. So my inlet, and let's just make that red. This is my fluid, and this comes in now at 350 Kelvin because I changed it over there. And I know that my utility comes in on this side. So this comes in at 298 Kelvin. So this is TU at V is equal to VRX. So where my V is equal to V min 1. So the last integration step must give me a utility temperature. So I want that TU min 1 out. Okay, at that last integration step, and that must be 298. And I am going to change my boundary condition for TU where V is equal to 0. I am going to play around with that, and my first guess, spelling, is equal to, and I just guessed there, I guessed the value of 320 Kelvin. And then I ran it. Okay, so there, check, and I checked. This is 303. But it shouldn't be 303, it must be 298. So that first guess of mine is incorrect. So I have to go back to the drawing board, and I played around with that first guess until it is that. And voila, it's about 298. And I am going to rest my case there. I am not going to worry about that 0.1 Kelvin. If you've got COVID and your fever goes up by 0.1 Kelvin, then you should worry. Okay, but not in this scenario. Okay, let's go back, stop sharing my screen. And questions. Okay, that makes sense. Okay, Philip, any questions? There are anybody else? Any questions that I missed? Missed questions? Okay, so me and Philip, we are wondering whether we still have some questions to answer. TU is the temperature where, nope. Let's just show it again. We'll do this. We'll keep on doing this until we get it right. Okay, so share screen. And it gives me practice. I can practice my skills in this. Big, don't worry. No sorries. Okay, so there we go. So this T naught, TU naught, is not the inlet. Oh, okay. So what is your question then? Your question is, this is the temperature. Sorry, my answer should have been yes. So I am being silly now. This TU naught, not the inlet utility temperature. It's not the inlet utility T. It is the temperature of the utility where T naught is equal to 350 in this case. Is 350 Kelvin. So where the reactant is set. Capiche? Okay, so let's see, stop sharing the screen, and I am going to go there. Check out, sorry Dean. Okay. Okay, yes, whatever. Logical reasoning can be tricky. You would want to run many profiles. Okay, so design tips. Get something to work first, even if it is an isothermal reactor. So even if you skip all that we've done in this course up till now, get a model for your reactor to work. Sort out your reaction kinetics. Normally, you will find information in literature that says it's best to operate this reactor at a temperature of 150 degrees Celsius. Model a reactor at that. And then you say, okay, but how feasible is it to keep it isothermal? Then you build in your energy balance. So I suggest, in terms of your own sanity and to reduce stress, is get a model that works. So you can get profiles for an isothermal reactor. Capiche? Now, yes, before you now start, because what is impacted by this heat exchanger design? What do I need to take into consideration? It is the effect of my tube diameters that I choose, the effect of the number of tubes that I choose on my linear velocity profiles through my reactor. Therefore, on my Reynolds numbers, on my Prandtl numbers, on that heat transfer parameter. So then you build up to whatever capacity you have so that you can achieve the minimum requirements. I could model a reactor, I could size it, it gave me realistic values for the size. I couldn't get to that integrated heat transfer. Then you will not get a distinction, but you will pass. Okay? If you want to get a distinction, you have to now start with different kinds of scenarios to say, okay, I played around with this, and the final design I choose may not necessarily be the one and only optimum, because optimum, what does it mean? There are many different goal functions that I can write to define optimum. It can mean that I want to increase selectivity. It can mean that I can increase productivity. It may mean that I can operate. So for instance, in this one, I'm going to share my screen again. A very important thing that I neglected there. If I look at my utility temperature there, I cannot just, if I use cooling water, I need to take cognizance of facts like I don't want the water to boil in my reactor. So I must make sure that my utility stays below the temperature of a certain value. So it is not a process where there will be one correct answer. If I have 1,000 students in the room, they will come up with 1,000 different designs, right? And that's why we sit together as teams normally when you work this out and say, listen, just build something. And of course, money is always coming in after you've now done your design and say, okay, this is the absolute best case. I want my reactor made out of gold. Says, no, okay, well, how will I do if it's stainless steel? And say, yes, okay, then I'm going to have 65% conversion. Then, okay, we'll live with that and rather build in a separator. So that's the whole design procedure for you. What I wanted to add here at the end, I think I'm not sure whether this runs now. So let's just see. Okay, so 100 liter, yeah. So am I sharing my screen or not?
Not yet.
Is that a yes? Sorry, I could just say again.
No, not yet.
Not yet. Oh my word. Okay, so share. So much for practicing. Okay, there we go. So a short calculation that I added here, for instance, is I have now chosen my tube diameters as an inch. I can now go and change that and see what the effect is. Now I must say, how many tubes do I want? If I have only one very long, thin tube, my reactor is going to be 203 meters long. So I just calculated that based on the geometry of my reactor. And that will earn you a fail. You will fail this design if you build me a 203 meter long reactor that has got an inch in diameter, right? So that is not feasible. But if I add, let's say I'm going to say 80 tubes, okay, then the length of the tube, and now I'm going to have to calculate my bundle diameter. So what's the bundle diameter? And I have to consider stuff like what's the pressure drop. And you all now realize that the number of tubes will change the pressure drop because I'm going to. So that's why go and pay attention, make sure that you can understand why the number of tubes will reduce the pressure drop, because I change my G, even if I don't change the tube diameter. And it's going to change my linear velocity. And as you will see next, after the linear velocity, it's going to impact on mass transfer. It can impact on the reactors where mass transfer to get your products to or from your catalyst surface. The linear velocity is a very important parameter. So if I increase the number of tubes, I reduce the linear velocity for the same flow rate of reactants that must flow through it. And that can impact on those design parameters. So it's fun. I think it's fun, and you've got the freedom to, within the limits of science and what is possible and what's realistic, and what is dangerous or not dangerous, to come up with something that says this is going to give me this kind of product, and that is why. And this is what I chose, and this is why I chose it. Okay, stop sharing. Cool. Questions? I can't see anything here. Nobody could. Okay, yes, Phil.
So the only thing that changes when we add the utility changes is for the counter current. We just need to remember that the TU naught that we give is actually at the end of the reactor.
From the perspective of the utility. So the TU naught that you give is the outlet temperature of the utility, but it comes out where everything else goes in, where you start your integration.
Yes, okay, but we don't really change anything else. We just add that negative.
No, we changed, no, yes, and the negative. So the energy balance of the utility also changes. Because because of that counter current effect. I'm sure you've done this in CIO, but I am not going to, you can go and revise this. I think you've done it in much more detail in CIO. If you do counter current kind of heat exchanger design, where it becomes a trial and error procedure, that your outlet temperature of the one fluid corresponds to the position at the inlet of the other fluid. So talking about a T naught utility, I think, as you suggested, maybe it's a misnomer. It's the TU at V is equal to the 100 liters, whatever you want to use. So that you, from the, or at V is equal to 0. Yeah, I'm confusing you. That T naught of the utility is at the point where V is equal to 0 from the perspective of the stuff that must react in my reactor. And then I must change that until at the point where my reactants and products mixture comes out of the reactor, the utility is what it actually is when it arrives from the pump where I get it from my cooling tower or whatever. Okay, happiness? Philip?
Just repeat that last bit, please. We change the TU naught, which is actually coming out, until the final. So the final integration of T utility is the inlet utility, actually, for a counter current.
Yeah.
And
The
that
outlet,
must
the
be
value that solve IVP. Okay, share screen, share. Cool. There we go. Check. Add a page. I want this to have more space. Okay. Am I sharing? Can you see my screen?
Yes.
Okay, so let's just draw this once again. So in other words, I know this is my reactor there. Okay, I feed my utility here at a utility temperature of 298 Kelvin. This is what I know about the utility because I've got a cooling tower, and it produces cooling water at 298. So this is where I pump my cooling water to that, and that will be a known parameter. Okay, then it flows.
Sorry, ma'am.
Yes.
So then we change our TU naught until the value returned by sulfur IVP is 298 Kelvin because we know that's our inlet. Okay.
Exactly, because solve IVP solves from volume is equal to 0 to 100. So I want this to correspond to 298. So this must be 298 there at 100. And therefore I must start guessing values for this value to say, okay, what must that temperature be? This one. What must this temperature be for my utility? Okay, and I call the TU naught. Okay, what must this be in order for this temperature to be 298? And it changes in this direction from the perspective of the fluid. But solve IVP calculates it from 0 to that in its integration because it exchanges heat. It exchanges heat with my fluid, of which the temperature starts at T naught, which is 350 or 320, the two scenarios that we considered in this design. Okay. Does it make sense now?
Yes, thank you.
Okay, all right. So even if you think I've got it, I think I may have it, the best is to play with it and to plot the figure so that you can see what happens in your reactor. Remember to avoid that pinch, that you don't have the utility. So pinch will look like something like that. If I cool this one down there, and my utility is something like that, that cannot happen. Cannot happen. There must be a difference for heat transfer. Remember CTD, we talked about that. Delta T required for heat transfer. We must maintain that throughout our reactor. Okay, right, let me stop sharing. Stop sharing. This is quite a long recording. I've got a question. Yeah, 10 degrees, reasonable. And remember, when you really are going into, yes, they cannot cross, they shall not cross. When you really go into heat exchanger design, we are doing it, we are doing it very peripherally. But I mean, in terms of the stuff that you learned in CIO for heat exchanger and the NTU, net heat transfer units and all that kind of things, because you must really make sure that your area is sufficient. And we use this approximation of this Taylor series for our utility temperature. So there you can delve deeper when you get to it. But yes, 10 degrees Celsius is reasonable, 5 degrees Celsius is reasonable, because remember, we account for that rate of heat transfer in our models. Because we say the rate of heat transfer is directly proportional to that gradient. So we are not going to, like in CTD, just guess a value to make sure that, okay, so because we don't take into consideration the U value and the area value. The U value is like a rate constant for heat transfer. So we have that, okay? So we have that rate constant for heat transfer available. So we can get by with less than 10 degrees if we've got a large enough U and an A value to suit our application. So at the inlet of my reactor, where my temperature of my fluids is nice and hot and I want the rate to be high, I don't mind that much if the heat transfer is horrible there, because I don't want that stuff to cool down there. So there, if I can get it closer to each other there in that realm, I will be quite happy to say, okay, I don't cool down as much there because I want to have the high rate. I want to utilize that high rate at the high temperature side of my reactor. Okay, let's see. More questions. Sure, this is a long recording. I apologize.